Hello. Today I will present my research on automated BIM LOD inferencing, a hybrid approach using knowledge graphs and multimodal LLM. My name is Taeyoon Kim and my professor is Ghang, and thank you for invitation for EC3. First of all, the background. In real BIM projects, specific LOD levels are often recurred through contracts, BEP, or client guidelines. In other words, LOD is not a theoretical modeling concept. It is used as a requirement that delivered BIM models must satisfy. And however, LOD is not assigned only once to the entire building. In practice, it can be recurred differently at the object or element level. Therefore, LOD checking means verifying whether each BIM object satisfies its required LOD. As the number of objects increases, manual review requires significant time and expert judgment, which motivates the automated LOD assessment. Then what criteria can be used to judge whether each object satisfies a specific LOD? To answer this question, this study adopts the BIM Forum LOD specification. It defines recurred elements for each object type and LOD level. In other words, LOD assessment is not just about the visual detail. It is about checking whether the recurred sub-elements exist. Then there are 4 challenges. The first one is the lack of explicit semantic labels in BIM subcomponents. Even when subcomponents exist in the model, they are often stored as a generic geometry or simple solids, making them difficult for machines to interpret. And the second one is the trade-off the visual BIM analysis. The raw BIM data suffers from occlusion, while decomposing every solid causes the fragmentation. This makes it difficult to identify meaningful components. And the third one is a high annotation demand for a BIM object classification. Previous studies have automated BIM object or LOG classification, but they mainly focus on overall geometry or object types. They are limited in verifying whether the recursive sub-elements for a specific LOD actually exists. The learning-based method also requires large amounts of label training data. Since LOD checking requires a sub-element level reasoning, the annotation burden becomes much higher than ordinary object classification. And the final challenge is insufficient granularity of BIM knowledge graphs. Knowledge graph and the ontology studies have contributed to structuring a BIM information, but they usually operate a larger scale, such as a IFC entity or object level information. In contrast, these studies requires a finer one, BIM subcomponents. So this is my proposed methods. Then the proposed methods consist of the 2 phases. The first phase constructs knowledge graph from the LOD specification, and the second phase uses the KG checklist and visual evidence to let the MLLM assess object LOD. The purpose of constructing the knowledge graph is to connect LOD specification, BIM entities, and actual subcomponents. This process was manually reviewed and constructed by humans, while the LLM supports the decomposition of ambiguous LOD terms into more concrete component candidates. For example, vague terms such as reinforcement assembly can be decomposed into reinforcement mesh or strut bars. In this way, the KG works as a semantic bridge between LOD documents and actual BIM data. Oh, I'm sorry. And the next step is geometry preprocessing. Material separation reveals hidden elements, and axis-aligned bounding box clustering regroups the fragmented solids into meaningful units. This creates semantic images that are easier for the MLLM to interpret. In the final verification stage, the KG checklist and semantic image are given to the MLLM together. The model checks whether the recurse of elements exists and then infers the object's LOD. And this video shows the rabbit-based implementation. When a user selects a BIM object, then the system generates visual evidence like that. And they load the checklist from their database, and they send the both visual evidence and checklist to the like a Gemini or a Sonnet, and they make some decision by MLLM like this. Then they make some clues, and they calculate how LOD is. And for validation, this study used a dataset based on the LOG dataset by Abodanian and Bowman. It includes 31 BIM families and 4 LOD levels. The validation focuses on the two components, converting natural language requirements into KG checklist and converting our raw images into semantic cluster images. The ablation study was designed as a 2x2 comparison. The two variables are whether the KG checklist is used and whether the cluster image is used. And the threshold calibration was also performed because MLLM-based visual verification is not a strict rule-based check. Due to occlusion and image resolution limits, some existing sub-elements may not be detected perfectly. Therefore, a decision boundary was needed to determine what proportion of a recursive element is sufficient for a target LOD. And the experiment concluded that the 40% threshold showed the best balance between self-check and rejection. And this is the results. Obviously, the KG plus cluster image settings achieved the best performance, 83.47% accuracy. But the thing is, overall many errors were in false negative cases. This means that the model was not mainly claiming that missing elements exist. Instead, it tended to reject cases when the evidence was uncertain. In the vanilla setting, the original LOD specification was evaluated sentence by sentence. Since one sentence can contain multiple conditions, the model tended to pass it only when all conditions were clear. And this led to low recall, about 22%. With KG only, the sentence was decomposed into checklist items, making the criteria clearer and increasing recall to about 52%. And in contrast, the cluster image only did not improve performance by itself, but it became meaningful when combined with KG. And this is my conclusion. This study turns ambiguous LOD specification text into checkable subcomponent criteria and converts BIM geometry into visual evidence that the MLLM can inspect. The first contribution is the LOD specific semantic bridge, which connects the LOD specification, BIM entities, and subcomponents. And second is a semantic geometry preprocessing, which reveals hidden elements and regroupes of the fragmented geometry. The third is combining these two outputs with an MLLM to verify LOD sub-elements without task-specific training. This experiment also showed the limitation. It's okay? A time? Okay. First, the limitation. First, the checklist needs the object-specific shape context. And the second, cumulative LOD checking can let a lower stage failure affect the later higher stage checks. And third, a simple threshold may not fully reflect the mandatory requirements of each LOD. So the future work should therefore add the shape context to the KG checklist and design prompts that reduce the cumulative checking errors and move toward mandatory requirement-based LOD decisions. And this is all of my research, and this is my contact. And thank you for listening my presentation.